50th anniversary of 4th, the 20th fourth day of this millennium, and the 19th of this century. I hear Yanni. People look at this and they say bad or good or whatnot, or they hear Laurel or Yanni. I happen to hear Yanni, and I'll say no more about the deep divisions in the land. Hooray, Rodney Reed. It may not go the way of Willie McGee. Willie McGee, when I was a lad, was a famous story. So check out Rodney Reed has a reprieve, sending the case back to the trial court. Today is not big game day, so we don't have to worry about a mad rush getting out of here. We do have a really big show, so I'm leaving out so much in favor of Dr. Ting. Are you setting? A man who literally needs scant introduction, Dr. Ting. Let me hand over.
He still has to do it himself.
Yes, that's right. I'm turning this off.
Okay. Yeah. Okay. All right. Hello, everybody. This is C.H. Ting, and welcome to the 4th day. And my topic this morning is living cells for computers. Well, I hope you would agree. And okay, actually for most of the time I prefer the PowerPoint than the blackboard or whiteboard. This time let me show you. This time I like to have the whiteboard. So here is our current understanding of biology. And this is basically what they call the essential dogma. And it states that all the genetic information moves from DNA to RNA and to produce protein. So this is the central theme in biology or microbiology. But this is really not a good picture, because the DNA, which coded RNA and which produces protein, in human being, it is only 1.5% of the genome. Okay, so this picture, what I want to show you, there's a 98.5% of DNA which is not used to produce protein. And why are they there? And so we know that lots of DNA are transcribed to RNA and then translated into protein. But over the year, people find lots of RNA. And an estimate is that there are up to almost 70% of the DNA is transcribed to RNA. But what for? Very few people know. So what they call this RNA non-coding RNA. And hence, those DNA which produces RNA are called non-coding DNA. And my interest is to find, well, are there really code in this thing? And what kind of code, in what kind of form? For one very interesting thing is that there are RNA, there are lots of different RNAs, very big RNA, very small RNA. And there are a whole bunch of microRNAs, which are very small. And earlier, people thought that these are these are mistakes when they try to analyze RNA. They just got some garbage and some fragments which is floating around. But then they found that lots of microRNA are actually functional, okay? And there are lots of them. Very few of them have been identified with a specific function, but there are lots of them. So this is the whole picture of microbiology. And the cell has the genome with DNA, and generally lots of information are copied down to RNA. And RNA goes out and do things which we don't fully understand. And among them, there's lots of microRNA there. So this is the this essential dogma really do not explain microbiology. Okay, it explains only the protein part of the microbiology, and so let's see, where is the okay? Come up. So to explain the entire picture, you need to understand the RNA, all aspects of RNA, okay, and not just a part which produces a protein. So what I'm proposing is this RNA dogma. So the whole picture, you need to consider all the RNA, okay? And now we have the genome, and the RNA, there are many different RNAs produced. I wanted to basically classify them as informational RNA and functional RNA. There are lots of RNA which act like enzymes, okay? And so they are functional. They have specific functions, just like a regular enzyme. But this messenger RNA is the what the central dogma is about. So DNA is transcribed into messenger RNA, and messenger RNA translates into protein. But there are other RNA, and there are lots of other functional RNA that we know: transfer RNA, ribosome RNA, and lots of microRNA. But I propose that lot more RNA are informational RNA. So they contain information. They do not have a specific function, but they do have information. And I would propose that the information in RNA will be released in the form of microRNA. And microRNA, they are small RNA molecules with 18 to 24 nucleotides. Okay, 18 to 24 nucleotides. That for example, 20 nucleotides. Each nucleotide has 2 bits of information because it encodes 4 different nucleotides. So a 20 nucleotide microRNA has the coding capacity of 40 bits. And 40 bits is enough to encode RNA for all the functions in all the genomes of all species. Okay, 40 bits are enough, but 32-bit is not. Okay, because 32-bit it would encode about, let me see, 4 billion. Yeah. And the human genome has 3 billion nucleotides. So that's equivalent to 6 billion code. Okay. So 32-bit certainly is not enough, but 40-bit seems to be enough. Okay. So I want to complete a whole picture by proposing that the microRNA goes back to the genome and select specific RNA to transcribe. Okay, so with the 40-bit code, you can go back to even the very big genome to select specific location and start transcription. Okay, so this way it's a loop. Okay, DNA to RNA and RNA back to DNA, and this will be this mechanism will explain all the complexity of living organism and all the different organisms. So, what I want, how do you prove it? Okay, or just get something to support this assertion. And so I studied lots of RNA. So I select 5 big, long non-coding RNA databases. So you can see this largest one has 400 megabytes of data. And these data, I believe, are not complete, and they are not very well understood or selected. So if I just go into the database and say, okay, select or delete all the duplicates, and I found that there are lots of duplicates, and I can remove them, and this is the number of RNAs which are not duplicates. So the fact that they have duplicates in it, there's a problem in them. And I also study the intersections between these databases, and their intersections are not very good. I think at most 20% or 25% of the database have overlap. So, our understanding of RNA is still very preliminary. And the way I analyze them is to reformat the data form, data file, and I convert them into tab-separated data files, and with the names, with a name field and a data field. So this data field can be thousands long. Okay, but Excel doesn't mind. It just displays the first few nucleotide here. It falls off the screen. But this is in this file, I can tell Excel delete all the duplicates, and Excel is very happy to do that. So that was very nice. So what I did was basically take this data file, all the data files, and separate them into a flat data file with all the nucleotide information, collecting a big flat file, and then generate an index file, which has the name and a pointer to the address of the specific RNA that's being put into the flat data file. So I have all the information about the various RNA can be accessed very conveniently through the index file. And the data file, when I put them in a flat data file, I can manipulate them very conveniently. And what I did was asking asking for 20 nucleotide patterns, repeated 20 nucleotide patterns. So I would go into this file and pick 20 nucleotide and ask, is this 20-bit pattern repeated? If it is, I will save it. If it is not, I will just ignore it. So going through the entire data file, pick a 20 nucleotide pattern and do the same thing. If they are repeated, I will save them. Okay, so this is the what I call the exhaustive pattern search. I will get and retain all repeated patterns, and I believe that's information. Okay, patterns which are not repeated generally are noise. Only those patterns which repeat contains valid information. And then you collect all the information, and then you can do your analysis. Okay, now I collect all the repeated patterns. There are billions, okay? And then I screen them, throw away all the non-repeated patterns, and save all the repeated. And if I sorted all these repeated patterns, what I call repeats, 20-bit repeats, and I would sort them according to the address in the big data file. And you can find lots of repeated patterns are consecutive, okay? And these consecutive repeat patterns are packed into what I call pairs, okay? And pairs has the information. Okay, here is one of the big database, and you can see that the repeated pattern. And here, first column is the address in the big flat data file, and the next is the name field. You see here, these are the index file, records in the index file. And these are the records in the per file, okay? So I inserted the index file back into the per file. And so you can see that these pairs are from each and different original RNA molecule. So you can see there's lots of long pairs, thousands of nucleotides. But the interesting thing is about these very short pairs, and these pairs form clusters, and the clusters are called necklaces. Okay, you got pairs, and you string up the necklaces. You got you string up the pairs. You got the necklaces. So when last year I was doing this in genome files, and in genome files the information is not that concentrated. But this year I said, well, the information in genome are not used completely. Only the information are selected and put into RNA. So analyzing RNA, you can get much better information from the gene than the genome itself. So here, with the RNA file, I found lots of pairs, and I think that shows that these are the information, and this information are organized very nicely in RNA molecules. So here, let me see. So So, okay, here is another. I want to show you the best necklace. Okay, and this is they're in 20 pearls streamed together, and in the second column is the distance from this pearl to the next one. So this shows how wide they are spaced. And this is the length of each pearls. And you see the pearls are variable length. I start with 20 nucleotide patterns. But if I find consecutive patterns, I just collect them into one pearl. So pearls are variable length. But you see these pearls are separated. They are separate almost 100. They are 31 nucleotide long, but separate by about 100 nucleotides. So this is the pattern I want to see. And so if the pearls generate microRNA, and the necklace are just a list of microRNA, and that's a program. And that's fourth program, okay? Because in fourth, we all we have primitive commands which would just go do things by itself using whatever the host machine is. And then we have lists, okay? All the compound high-level colon definitions are just lists of other instructions. And I think this is the list of instructions. Okay, so I would claim that cells are fourth computers. And pearls are repeated patterns. And the repeated pattern, I believe they contain information. Okay, and pearls are stringed together into necklaces. And necklaces are cluster of pearls, and they are actual programs in genome. So pearls are instructions in a cell computer, and necklaces are lists in a cell computer. Cells are therefore fourth computers. And then God is a fourth programmer because he wrote all these things. Okay, with that, I wish you all a happy 4th day. Thank you. Any comments? Any questions? Yes. Say it again.
How did you find the duplicates?
Okay, that was the exhaustive. Okay, the question is how do you find duplicates? Okay, the duplicates are the exhaustive pattern search. Compare a 20-bit pattern with all the other 20-bit patterns. If they are the same, keep it in a file. If they are not, I just go on to the next one. Okay. This way, I would find all repeated 20 nucleotide patterns, and that's a base. I'm thinking that I will pick 20 nucleotide patterns because if I just random noise, it will avoid random noise. Okay, and if random noise, they are 40 bits. If 40 bits of a pattern matches, it's got to have something there. It got to have information in it. Okay. 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 Thank you very much. I think let's just move on.
Okay, let me repeat while Ken makes his way to the front. Let me repeat clip the mic to your shirt. Don't hold it in your hand. And introduce yourself. And when you take questions, bring your slides down for the next guy to plug his computer into the projector. And stand next to the guy that's asking the questions so that you don't have to repeat it. You've got to find if the questioner does not.
Okay, who's next?
Ken is. He's making his way to the front of the room.
Just need a couple minutes.
Andy, you're up after Ken, so.
Where will I sit up there?
Yeah, in a little while, half an hour.
Would it be okay if we swapped?
Swap. Are you ready to go right now, Andy?
Yeah, okay.
Oh, slackers and ne'er-do-wells. Andy, why don't you start? Ken?
A friend is coming. Oh, Chuck.
Oh, okay, so you're not ready to start. Ted, you're on the hook. Sorry.
Okay. Okay.
I got a complaint on the meetup that the calendar agenda on Wednesday was the fabulous October meeting. And I responded and tried to be civil and polite.
Thank you.
I had some personal problems, but now the actual agenda for actual fourth day is available online. I think that when I sent it out to the actual speakers, I made some comments about, there was actually one where we started the meeting and then the agenda was posted during the actual meeting. That was a little less organized than it could possibly have been. But this was Thursday, plenty of time. If you haven't had any coffee, now's a good time. In the coffee over there. They're all the same. Are you sure?
Red light's on.
Okay.
I'm set.
We're back on, folks.
Good morning, ladies and gentlemen. It's my pleasure and privilege to be here for fourth day. I got into San Francisco from a London flight just on Thursday evening, and I'm not quite over my jet lag, so it's great to be back here in the Bay again. So I'm going to be talking about the Gigatron TTL computer. My name is Ken Boak. I'm a hardware engineer based in the southern part of the UK. I've been interested in Forth probably since I was about 15. A follow-on from the August 1980 Byte article that a school friend of mine told me about. So I've brought some props. I'm going to be passing this around for you to have a look at. You're welcome to prod it and look at it. And I'll be talking about the Gigatron, which is an 8-bit machine built entirely from TTL. And I'm going to talk about the hardware, and then I'm going to talk about porting Forth onto a very unusual platform. So let me take you on a brief journey in ancient history. Some of you will be familiar with this. I believe this is where it all started. As far as our current thread of computer technology is concerned. September of 1975, MOS technology introducing the 6502, and young Steve Wozniak purchasing one of those processors at Westcon, realizing that this was going to be the game changer, and plugging it into the small computer that he was already developing that I believe was 6800 based. And within a few months, the result was the Apple I. So from this point on, the rest is history. But also in the middle of 1975, the existing technology was TTL. TTL had been around since the early 60s, and by the mid-1970s it was the standard go-to logic for whatever you wanted to build. And it had reached the point where it was cheap enough, and it was used widely in mini computers. And the example I've got here is a CPU card from a Data General Nova. These boards were, I think, something like 15 inches square and held about 100 TTL chips. So that was not quite state-of-the-art in 1975. The LSI 11 had appeared in the spring of 75, which integrated a lot of the PDP architecture onto 4 or 5 VLSI chips. But this kind of sets the scene where we were 40-something years ago. So back in 2017, I got to hear about this guy. This is Marcel Van Kovac. He is a software engineer based in the Netherlands, and he had a bit of a hardware itch to scratch, and he decided that he would construct a machine entirely made from TTL. And not just a very simple machine, but something that would have a full software suite behind it, and color video and sound. And so he researched TTL logic for a number of months, played around with a few chips, had some ideas and aspirations from other designs, and he wanted to design a CPU that avoided using the more sophisticated and now obsolete devices such as the 74181 ALU. And from the outstart, he wanted a highly integrated design where the CPU and the video generation hardware were basically very tightly coupled together. It's a Harvard design, not the easiest for Forth, and he wanted to achieve it in fewer than 40 ICs. So this is how it started. A great big bunch of breadboards, 40 chips, and this was taken when he was first bringing it up, and managed to get some color bar video out of it. His design was inspired by the Apple I, but it's smaller, cheaper, more colorful, and faster. So here we have the breadboard. Switch to spectacle mode. Okay, at the top here we've got the program counter, a couple of ROMs, we've got the memory access units, we've got the RAM down here. In amongst all this orange, this is the ALU, we've got an accumulator, various other registers, and this grey area up in the top here, that's the control unit. From the breadboard came the two-layer PCB, nicely labeled. We've got the ALU and accumulator occupying this area on the left. Program counter is above the ROM here. The X and Y registers that access the video RAM. We've got instruction register, and this is the instruction decoding here, which uses a diode ROM array. So nice and simple. Just very quickly, for simplicity in hardware, it was built as a Harvard architecture. It's clocked at 6 1/4 megahertz to meet the timing requirements of VGA. And it's got a very simple pipeline so that it's executing one instruction per clock cycle. There is the bus architecture. We've got the ALU in orange, we've got the main data bus around the outside in blue, we've got the RAM in red, the memory access unit, the ROM, the program counter in green, and a simple input, which is a shift register to take the output from a keyboard, and the output register sends 8-bit data to the video D2A converter. Okay, so from the outset, Marcel wanted to use very simple TTL devices. It's mainly multiplexers, counters, a few logic gates, and a shift register. And with the exception of the modern ROM and RAM, all of those devices would be available back in 1975. And at that time, those devices would have probably cost between $1 and $3 a piece. RAM was still very expensive at that time. I looked up the byte archive, and 4 kilobytes would cost you just shy of $100 back then. So there's another view of the PCB showing the various buses and the architecture. A simple instruction set. It has an 8-bit wide instruction word. This consists of a 3-bit opcode, a 3-bit field to define the mode, and a 2-bit field to define the source of data that is going onto the bus. that's basically the instruction decoding. You've got the operations on your left there, the addressing mode in the middle, and the source of the data. Okay, the control unit is very minimal. It's only 6 TTL devices, mostly, well, there's a couple of 3 to 8 line decoders there, and each of the little black diamonds, that is a diode junction, like depicted in the bottom left there. And there's part of the diode array, and you've got the 3 to 8 line decoder at the bottom there, and you can literally view the instruction decoding by the positioning of the diodes. All nice and simple stuff. Okay, so because the 74181 is no longer available, Marcel had to come up with an alternative for the ALU, and he wanted all the usual instructions, the usual logic and arithmetic functions. So we've got add and subtract, and, or, and XOR. And so the solution lay in a rather interesting technique using the humble 4-to-1 multiplexer. So this is what you've got inside a 74153. Normally you've got 4 inputs there on the left, I0 to I3. You've got a couple of select lines, A and B, and whichever you choose appears on the Q output. However, there's a different way of using the multiplexer. You can connect your A and B to a couple of your bit lines, and then you can feed a pattern in on I0 to I3, and what comes out of Q is one of the 16 common logic functions, one of which will be AND, one will be OR, one will be XOR, and then you can have A by itself, complement of A, and so you, with just very simple hardware, you have a very rich ALU. Okay, so you take 8 of these multiplexers, you put them all together, and you feed your bit lines in the top, A0 to A7 and B0 to B7, and you feed your opcode into I0 to I3. And that gives you the logic part. Then if you take 2 of these logic units and a 4-bit adder, an 8-bit adder, that will provide your addition and subtraction facility. And conveniently, you get 2 of these logic units in each of those multiplexers, so it's quite economical in chips. So your 8-bit ALU is 8 multiplexers and a couple of 4-bit adders. Okay, very quickly, the video generation hardware. You've basically got a RAM that's containing your picture. You've got 2 registers that address it, the X and the Y, that basically define the coordinates of the pixel that you want to write to the screen. The X register is an 8-bit counter, and so you just increment that to basically push the next pixel out to the video DAC. And then the Y register selects the line that you want to push out. So it's all very simple. So we've got essentially a resistor network there to give you 4 different levels of red, green, and blue. It's 2 bits for each of the red, green, and blue. And the other 2 bits in the video byte, they are used to contain the horizontal sync and the vertical sync. And then at the top there, we've got the audio reconstruction DAC. In that resistor network called DAC, that's a an R2R ladder, and then we've got a couple of capacitors to form a high-pass and low-pass filter, and then straight out to a jack. Okay, so the hardware architecture is not the easiest to program. Working in 8-bit native assembly language, which has to be cycle accurate to meet the horizontal and vertical video timings, it's not a job that you want to do more than once. So on top of the hardware architecture, Marcel built a 16-bit von Neumann architecture, which he calls vCPU, the virtual CPU. And into the native 8-bit assembly language, he's coded up 37 useful instructions like 16-bit add, 16-bit subtract, and various operations to manipulate the stack pointer, and basically he creates a simple CPU model with a 16-bit accumulator, program counter, an 8-bit stack pointer, and a 16-bit link register. Now, all of those instructions are cycle accurate, so that if you are approaching the point in your program where you need to put out a horizontal sync, that instruction will be paused until you emit the horizontal sync, and then it will carry on. So all instructions are between 14 and 28 native clock cycles, so that puts them in between 2¼ and 4½ microseconds. Okay, that's a breakdown of the instruction set. In the hash C, that's the number of clock cycles that they execute in. The longest are is the 16-bit add with carry. Okay, so we've got this 16-bit von Neumann architecture. We need to try and build on top of that a fourth virtual machine. So we can start to make use of the existing vCPU, and we can start to code in some of our fourth primitives. There we've got the next primitive, where we're adding the instruction pointer to the accumulator. We're storing it, then we're reading the word from there, which gets us the address of the code field, and then we're jumping to that code field address. And so similarly, further primitives can be added fairly easily using this 16-bit virtual CPU. And there we have the starts of a little fourth shell with a few test words displayed on the screen. So this is very much a work in progress, and if anyone would like to take up the challenge of extending this, please come and talk to me later in the day. So let me tell you a bit about the Gigatron community. It's a vibrant community all over the world. The Gigatron is sold as a kit, and in the last 18 months, approximately 750 have been sold. Several have been sold particularly into this area. They've gone to all the headquarters of the well-known tech firms here in the valley. There is a C compiler for it. We've got a port of Tiny Basic. And the hardware is being extended to support a modern SD card by bit banging SPI. And one of the later projects is to actually emulate the 6502 on the virtual CPU. And the proof of concept is being able to put Commodore BASIC in. Admittedly, we don't have a lot of RAM left, but you've there got the reciprocal of 7, which in original Commodore BASIC was, I think it was 40-bit floating point. So all this is emulated on a bag of under 40 TTL chips. There's a screenshot of Tiny Basic, and one of the self-hosted tools is a variant of Wasmon, which is a simple hex monitor and editor. There's an emulator which allows you to code up either in native assembler or the vCPU. And there's the native assembler. And that's it. So are there any questions?
What is the interest that the tech companies have in this? Why are they interested?
Okay, I think it's for people that are maybe working in the tech industry that want a little hobby project, something to solder up with their kids. I heard that Google, Facebook, and Amazon, these kits have been sent to their headquarters there.
So is that educational?
Educational, yes. Yeah. Yeah.
Very, very cool. I love it.
Excellent. Any more? Okay, I just have one last remark to make. So, Chuck, I'm sorry I missed your birthday last year when you were in Edinburgh. And on behalf of Fourthers all around the world, I'd like you to accept this gift. Thank you very much.
I think you should set up on that table and just roll it across when you're ready to go.
Okay.
All right, so we're going to take another short break, and if yeah, thank you. Those people, it's actually off, so it doesn't matter. But we're going to take another short break. So coffee's there, pastry or donuts or California grizzly bear claws or something. I'm not sure what the. Oh no, those are extinct. Never mind. It reminds me, you've probably heard me say, oh, these kids today, none of them have a pocket knife when they need it. There's a certain thing in the corporate world, you go to a meeting and everybody should have a pen. If for no other reason than if it's training especially, you need to sign the list that says you took this training. There's a bunch of interns at this place that I was working, and they all showed up, and not a damn one of them had a pen.
Who needs a pen?
All right. When you're ready to go, Andy, just hook this to your shirt. It's an IQ test. There's a button there. Of course, unlocked.
You need that? That for the phone here.
Yeah, I need it.
it's nice to see some overlap with para.
Wi-Fi working on it. So it talks to your robotic.
I don't know if you remember me. Yeah, okay, John. Yeah, Alpha India 6 Sierra Zulu. Yeah, I see Henry in the back there. Yeah, right. Yeah.
So it has way too much resources for
There's a little DF demo here.
it's got
You wrote that in Fork?
$3 for the system on module.
Is it gonna be another 5 minutes or what?
Look up everything. Yeah, you want somebody else to talk first?
I wanted you to start on time. Joe?
$3. It's free for one key. Come next year, it's the intelligent fourth robots when they're in. And we're gonna port my OS on it. Well, it'll just be software. I am doing FPJ work on work, which I'll talk about soon. Yeah, so it'll all be software. You're thinking more like FPJ, right? Or some of the AI chips.
You need to connect to the HDMI?
So,
Yeah, see, that's my screen.
Okay.
and we're gonna be able to hook them into this. So,
Okay, but you get this first, then. And then I get it.
Oh, you want to take over then?
No, you go ahead. I'll talk after you.
Okay, sure.
I have to hook up everything.
All right, I don't think I need, I don't even think I have that hit me thing. Yeah. So, I'm just going to use
Voice recognition for Canadians, $50 for voice recognition. Remember in 1990, it was a $2,000 board that plugged into a PC. Yeah, I had one. It was because I was trying to, all my robots were boards, so it's a no-brainer. If you have a voice to text, there's no hardware, there's no even code development. If we can get that, but now they have it for $50. So that will be used too.
John, Strick, Andy, Ting, stop talking.
Can everyone hear me? You all set to go?
Andy, stop making noise. Joe, would you please
Thank you.
introduce yourself?
Okay. My name is Joseph O'Connor. I'm here to present A Tale of Two Fourths.
It's
Tim.
not nap time yet. It's too late by many, many years.
Okay.
Oh, why? That's good.
Okay, I'm sorry.
All right, we all set to go? All right, some background. I first encountered Forth in the early 1990s. I came upon Tom Zimmer's FPC. I found it was very helpful for my assembly language homework assignments. First I'd write it in Forth, and then I'd write it in TASM assembler or whatever assembler that I used. Okay, sorry. Okay, I'm letting it rip.
Thank you.
Okay. Right. My first exposure to Forth was in the 1990s with FPC with Tom Zimmer. I found it very helpful in doing my assembly language homework. So first I'd do my assignment in Forth, then I'd translate it into assembler. Sometime after that, I encountered Norman Smith's Until. I was very interested in that. It's a Forth compiler written in C++. And it was a bit unusual in its setup in that it wasn't meant to run standalone, although it can. But its real power is an application language that sits on top of a program. It can be used as an extension language or a DSL. Okay, so, well, this inspired me to write my own version of Forth. I figured if he could do it, I could do it. However, at the time, I wasn't really using C++ anymore. I found the compile times too slow, so I had switched to Delphi. So I wrote it in Delphi instead. All right. Here's some brief Creole Forth history. The focus is on writing a DSL. As of 2019, there are 4 different versions: Delphi, Excel, JavaScript, and Python. So this presentation is going to be concentrating on the JavaScript and Python versions since I just wrote them. So what we have here are the primary moving parts. These are common in all of the different Forths I've written. First, you have the stacks. Obviously, every Forth has that. The dictionary. I have a regular dictionary, which is an associative array. And then I have a reverse lookup dictionary, which is integer-based. I use that for lookup in the parameter field. Then what I have is I have a global simple props. This is an object that I use to pass information from one subroutine to another. It's very complicated. I won't get into it too much. Creole Forth words. These are what our fourth words are made out of. So you have the name field, the code field, the parameter field, the link field, etc. Then, last but not least, you have a Creole fourth bundle. This is an assemblage of all of the above. There's usually one per application. It doesn't have to be that way. If you're programming something really complicated, you might use more than one bundle. It's also used by the colon compiler for temporary storage. So I have two Creole fourth bundles that I work with when I do colon compiling. So these are the stacks. I have the data or parameter stack, return stack, the vocabulary stack. I have two others, the pre-filter and the post-filter stack. That's only really developed in one version, the first one. Dictionary has two parts. You have the regular associative array dictionary, so it looks up a name and it finds a value. Then you have a reverse lookup dictionary, which is integer based. That's used for parameter field lookup. So setup allows the colon compiler to store integer tokens in the parameter field. They're looked up by the do colon method. Okay, bigger. Control structures. The standard ones, if, else, then, begin until, do loop. For do loop, I have I, j, and k as integer indexes. They're built in. Some other features, single line comments. This is a backslash in JavaScript and a / in Python. I had problems with parsing when I was using a backslash, so I switched to a /. Multi-line comments, those are the parentheses. There's a help field, which I use in VList. This is what they don't have, at least the JavaScript and the Python versions don't have. Forget. With JavaScript in particular, you forget everything with one page refresh. So I didn't feel any compelling need for forget. Doesn't have a lot of return stack primitives like rdrop. I found no compelling need for them. Compile, bracket compile, and postpone. I don't have them in JavaScript and the Python versions. I do have them in the Delphi version. Recursion, I don't have them in the JavaScript or Python versions. I have them in the Delphi versions. I didn't find any compelling need to use them. It also doesn't have as many words as most force. It has less than 100 for the core system. Creole fourth execution. So first the words are parsed using a do parse input routine after they're put in the input field. Then they're passed off to the do outer routine. The do outer, what it does is it looks up the words one at a time in each vocabulary. As soon as it finds a match, it stops the lookup process and it executes the word. If it finds no match, then the word is pushed onto the stack. There's no type conversion done at all. It's pushed on as is. There are 4 types of words that I work with. Primitives, these are defined in the core language. So if I'm working with Python, I define the primitive in Python. If I'm working in JavaScript, I define the primitive in JavaScript. High-level definitions, these are defined with the colon compiler. These are assemblages of either primitives or other high-level definitions. So I have compiling words. These are for the control structures mostly, if, else, then, etc. So I have one routine for compilation and another word for execution. Defining words, these are defined with create and does. So far, I only have variable and constant. So the colon compiler, it's a bit unusual, has no state variable. Compilation, it starts, the immediate vocabulary is pushed onto the stack. It ends when the semicolon is encountered. So all immediate words are in the immediate vocabulary. This is always search first. So from the point of view of the colon compiler, words are grouped into three classes: comp and PF, execute, and exec0. Comp and PF, it's just compiled directly into the parameter field. It's really a synonym for comma. Execute, it's executed. That's for compiling words. And exec0, I use that for comments. All it does is move the outer pointer to a different point in the input stream. So this is what the pad area looks like during colon compilation. The word looks like the word 5 column. It actually isn't there. I just use it to make things clearer. The token and action are there. So if I look up the word if, it sees the token 52 and it puts it in the parameter field, and next to it, it puts its action execute, because that's a compiling word. Hello, its token is 5 and its action is comp and PF. So that's just compiled directly into the parameter field. Else has an execute token because it's a compiling word. Tulip is a regular comp and PF word, so it has the 6 goes into the parameter field, and then 54, it's executed. Any code there is executed and placed into the parameter field. So for words with a comp in PF or execute action, the compiler puts its address in the pad area next to its associated action. Words with an exec0 action simply move the outer interpreter past their closing delimiter. So once the words are all looked up onto the stack, what happens is that they're passed on to the regular interpreter, and it's just executed like a regular routine. So JavaScript versus Python, some similarities, some differences. JavaScript has object-oriented programming, but what it has is it's called prototype object-oriented programming. So it has no classes. You simply make a copy of an existing class if you want inheritance, and you add some more properties. It's a little bit simpler than the normal type of OOP you might see. Python, it's more conventionally class-based. In spite of this, the structures of the two compilers, they're very similar. I'd like to show them to you. JavaScript's flexibility allows adding syntactic sugar. You can make it look like other languages. So it resembles conventional OOP. Okay. So left side is JavaScript, right side is Python. So you have the do+ method in JavaScript. You have a check for the arguments, and on the right in Python you don't need this check, but you have some type conversion. That's really the only difference. As you can see, they're very, very similar in structure. All right. If I can scroll to the bottom. Okay. All right, so you see they both have a build primitive routine. I don't know how this got out of sync. Okay. So only difference is the JavaScript one begins with a capital letter, but they have the same parameters. Structure is very similar. These are some challenges I encountered when coding in JavaScript. Biggest one by far was detecting stack underflow. I use arrays for the stacks, and the problem is if you pop off an empty array, you'll get an undefined object, but you will get something. So that made stack detection of underflow very difficult. The default array behavior can be overridden, but that's generally not a good idea. So this is a strategy that I adopted: is have the primitives detect the data stack, and they can do their own stack checking. Python's challenges were a little bit different. JavaScript is very easygoing with type checking. Usually that helped me. Python's is much stricter, so I had to be a lot more careful about type conversion. So for that reason, the literals, when I do like a create does, I only work with numbers right now. I'm probably going to have to put in some more work to work with strings. So if you want to use Creel 4th for JavaScript for yourself, easiest way to do it is just reference it in our web page. So that's my pointer to get my GitHub repository. So, but you don't have to put it there. You can put it on your own file system. It doesn't require a web server, and you can use it with other libraries, jQuery, Angular, but it's not necessary. I've also used it with Node. It's a little bit tricky because of Node's event looping. To use Creel 4th for Python, you can either embed it in Python code. So you have an input area you set to the code that you want to process. You call it doParseInput, and then you call it doOuter. Or you can run from a script. I have a script on my GitHub repository that you can use. That's its name. Here's where you can get them if you like. Or If you rather just try out Creo 4th for JavaScript, you can do it online. I have a web page for that. I don't have one set up for Python yet. Okay, I'd like to give a short demo. All right, that's actually the wrong web page, but that's okay. So we'll start with vlist. Hard to see. Okay. All right. So just gives a dump of the contents of the dictionary, puts it into HTML. If you scroll down to the bottom, currently there are 84 words defined. All right, I'll clear this. Next one up, hello. So that just pops up in dialog box, hello world. So it executed this word. Some arithmetic. Okay, one thing, it's possible to turn the parameter checking off. If you would like to do that, you just have to be sure that your stack arguments are all set. You don't have too many or too few. Because if you have too few, this is what's going to happen. All right. Okay. I think I'll skip the eval. Eval just evaluates JavaScript code. One. Okay, that's a very simple script. All it has is the hello primitive in it. Second one does vlist. That just it does a dump of the dictionary contents, just like we saw in JavaScript. Script 3 is a test word. Okay, I guess you can't see it too well. There. So, this is a high-level definition test 1. You should get hello. If you pass 0. So, let's pass 0. See what happens. Oops. Okay. Okay. So, what you see here is the else clause adds 3 and 4. If you go to the output, you'll see 7. So, you can see that it correctly executed. Yeah.
You're up against it. Maybe take a couple of questions while Andy gets plugged into the projector.
Okay, sure. Okay. Yeah.
Stand next to the questioner so they can hear you through the microphone.
You mentioned that you have several stacks. One of the ones I noticed, you say you have a vocabulary stack.
That's correct.
Now that means you could save vocabulary on it, meaning like the head of a vocabulary, you can put it on there?
Yeah, you could define any vocabulary that you want. I usually define an app spec vocabulary that a developer would use to put on his stuff to distinguish between the only and fourth vocabularies.
Right. So in order to go switching between vocabularies, all you have to do, you could do a swap or a roll or, a pick or...
I use the definitions
That's what I mean.
word.
But you can switch between these.
Yes, you can.
But you can do it very quickly then.
Yes.
That is, I like that concept.
Thank you.
That is,
It's not mine. I read it in Martin Tracy's book.
Oh, okay, Martin Tracy. All right. How come Chuck didn't invent it?
I thought he did.
Well, vocabulary stack?
I don't know if he...
It was different
I got the idea of the immediate vocabulary from Chuck.
Ahoy, Joe, question?
Yeah.
Your VList word outputs into a table.
Yeah,
So,
HTML table.
Is the document model exposed in the fourth system so that you can do that?
Well, it's on the web, so all it does is code a table using.
But is the fourth system able to generate HTML into the document?
Yeah, you can see it does it right away.
For no purpose, it's not just for the VList word, specific to the VList word.
You could define any primitive to generate. Yeah.
Okay.
All right. You could define a primitive to do it and assemble them into high-level definitions.
All right.
Yeah.
So I think I have a similar question.
Mm-hmm.
You had a Creole fourth output page in HTML.
Mm-hmm.
Is that coded in fourth, that entire page, and output to HTML, or is it JavaScript that's taking the output of the fourth?
I plug in my JavaScript Creole fourth into a web page. I do a reference using the source key script and source, and then I output it to the specific HTML page.
So as an example, you have a column labeled stack.
Yes.
Does that header, the word stack there, does that word come from fourth?
Yeah.
Or is it from JavaScript shell around fourth?
It comes from the that word for VList, it comes from the internal data structures names, I believe. So, yes. Am I done? Okay.
Would have been time we're not so this. Yes.
I understand. I've forgotten something.
Raspberry Pi is not putting out for some reason. It's put in your shirt pocket? Okay. Is it working? Not working? Okay. For some reason, the Raspberry Pi is not pushing video out.
Sam has a suggestion. If you unplug the HDMI with the unit on, or if you boot it up without HDMI plugged in, it will be off permanently. So you'll need to power down the Raspberry Pi, make sure that HDMI is plugged in, and then power it back on.
Okay. Okay, I unplugged it. All right, the green light's flashing. Oh, yeah. Okay, good. All right.
Yeah, that's an issue with the Broadcom too.
Okay, so I'm using G4. Let's see. Oh. Hello? I have to talk loud?
Yes, but when I say speak to us all in this group, we want to hear you here.
Okay,
Get your hands on the mic, don't worry about it.
okay. I just have to talk loud? Okay. All right, so, well, and let me get started by saying that I guess Bill Ragsdale had something similar, a Doppler direction finder. He gave me a handout here that from
2008. I must have been at that meeting, but my memory is so bad. I'm 83 now, trying to keep my brain working doing this. And anyway, so this is a kind of same thing, but this is using a G-Force on a Raspberry Pi, and Bill's, I guess, Bill, is that a PIC chip?
Arduino, Andy.
Arduino, okay, and much slower. So my intent was to grab these Doppler bearings, which I can't demonstrate to you because I forgot. I left one receiver in my trunk of the car, and it's like 12-minute walk. We parked in the wrong place, and so I don't have any of my radios, and two hams here. Shri, do you have a radio that has a 3.5 millimeter output? Probably not. He's got a Baofeng. Yeah. So I don't have a 3.5 millimeter audio source. Huh?
Just tell us about it.
Yeah, okay. So anyway, I have an interface cable here taking the four lines that define which one of these 16 LEDs comes on. And now, when this thing gets a bearing, it points to one of these LEDs, or maybe it flutters around a little bit. So 4 lines plus a strobe line, which defines where to set this thing, go into here, and then some other wires that I wanted to look at into the Raspberry Pi. Okay, now let me get, somebody give me a radio that's got a,
I don't know if it's got the right frequency.
where's the 3.5 millimeter audio output? Oh, maybe. How do you unsquelch this radio? I need a broadband noise.
Second button from the bottom.
Yeah, you set it up while I talk.
Get up there.
Okay. So, okay, and
It's brand new. You probably know more about it than I do.
no, I don't know that one. Okay, so while you're doing that, let me bring up the G-Force and the, let's see. Okay.
Okay, Squelch, where do you want it?
All right, just, can you put it on UHF 442.9? Because I can key up on that frequency with this radio to show you how it works. Makes noise. Okay. This one?
I hope so.
Yeah, there it goes. Make it loud. Where's the volume?
You have to change that one.
Make it real loud. Oh, I think it's working. Yeah, maybe that's loud enough. When it gets too loud,
It seems to have shorted something, I would say. Oh, wait a minute.
I can tell here. No, I don't hear anything.
Yeah,
The speaker's
it's
gonna
off. Hold on. Okay, volume up.
squelch, unsquelch.
Squelch is
Okay, it's not working, huh? I don't hear anything there.
Yeah.
Well-
How many pins on your input?
3.
Okay, that should be working. Yeah.
Is it working? I don't hear anything. Anyway, so, okay, now let's go to, let's see, Pi. Let's see, where's the media? Media, there, okay. Media, Pi. Huh. Let's see, where's my code? It's on this Lexar thing. Let's see. Pi. heck is it? Oh, Magic Pi, I think it's here. No, downloads. Good heavens, where is that Lexar chip? Let's see. Media? Oh, there. Yeah. Fourth source code. Fourth source code here. Okay. Now here's my latest one. Henry back over there, if anybody wants to see the text printed, Henry's got a copy there at the last row. Okay, now that's my source code. Okay, now the advantage of this Raspberry Pi is, oh, by the way, the G4 has 3 different ways to run it. G4-fast is the one I used to get maximum speed. G4-ITC is instruction threaded code anyway, and dash, just G4 standard is not very fast. I did some timings here. See, if I type these test words, G4 fast on Dev1 runs actually on my HP Mini that Sri helped me turn into a Linux machine. That one runs 50 times faster, but this thing, the G4 fast, will put out about a 1 megahertz frequency square wave. Now, I heard that you can actually do faster if you write assembler code, and you can go up. Some radio ham made a 14 megahertz transmitter out of a Raspberry Pi, but that's fairly tricky. Anyway, but the G4 is very fast, much faster than the PIC chip type. Now, the thing is, this thing samples the audio 500 times a second. So I had to grab the data and do a lot of processing, and very adequate for that job. Too bad I can't show you the thing running. If I go here, and let's see. CD, let's see, where is it? Okay, let's go. Let's forget these things. Okay. It takes too long to find it. Let's see. Well, let's just run. I got to get to that directory where this is. Anyway, just run G4 fast. Fast. Okay. By the way, this doesn't have vlist. It's mostly standard fourth, the latest standard fourth, but it has words. Very fast, huh? Let's see now. I don't want to take too much time trying to find my directory here, but Henry, are you good at this? Can you find my directory?
Can I find your directory? I'm not sure I can.
Okay, let's see.
What directory?
My source code. See how it took me so long to find it? I just run this all day, leave it on, and I forgot how to find it.
Okay,
Okay.
did you have a shell there? It starts with DDF, right?
Yeah, you know how to find something?
Yeah, I can run a find. Find dot dash name
I'm new to Linux.
DDF star. Under fourth code under downloads.
Yeah, can we go to that?
Go to downloads, or you want to do it individual? Is that it?
Yeah. Go to the Lexar chip. The Lexar thumb drive. Yeah, that's the
Fourth
one.
source
So,
code?
yeah, right.
Okay. I don't know where these arrows are.
Yeah, that's the one. Okay, yeah, now go to number 20. Type G4th ITC, dash ITC.
Dash ITC.
No, dash next to G4th. ITC, a space, and then DDF1 bearings capture 20.
Okay.
Yeah. Okay, good. So now we got it. Okay, so now type SSS.
SSS.
Yeah, enter. Oh,
There's your stack check.
it won't run because it can't run because there's no audio here. Oh yeah, there it goes. Oh, here we go.
I heard something.
Yeah. Let's see. Anyway, it's can we make this larger?
Yeah.
How do we make this
You want larger, or do you want more lines visible?
just larger?
Okay.
Yeah, just expand the window so.
Yeah. Actually, you were on it. Yeah, that was
Okay. Okay. Now, when this is just showing the data 500 times per second, but divided by 50, so that every 50 are showing. Come on, it's stupid. It's not showing it. But anyway, what it'll do, it shows the 16 slots, and when it's pointed, like right now, it's pointed somewhere. It should kind of show those slots having high numbers. Okay, I really can't show it working then, but okay. So if you hit Q, it should stop. Oh.
Oh, there's more. Huh.
Okay, because now if you do this for capture bearings, again, it doesn't run. Oh, there, okay. See, this is for debugging. You can tell how many, what microseconds you got a bearing, and it's trying to qualify bearings. It should be qualifying that guy. Yeah, okay. All right, good. So let's go look at the source code again. So what do we do? Just make this.
Click in the margin there, yeah.
No, I want to. Oh yeah. Okay. Good. All right. So this G4th is really good. It's oh yeah. I guess I'm not online here. If I plugged in the internet, I could go to an. Let's see. I don't know if I'm on. This doesn't have Wi-Fi. This Raspberry Pi, so I can't go to the internet here, I guess. But all right, forget that one. Yeah.
Yeah, you're offline.
I am? Okay, dictionary, G4th. There, oh, it's working. Okay. It has great documentation. and it has object-oriented programming, but I didn't use it. By the way, in my program, I never used any fancy features of Forth. Very straightforward, simple job. Okay, let's go back to my code. So I go like this, right? Cancel. Oh, please connect to the internet. Well, I got some of the things on my Pi. Let's go back to the other. How do we go back to the other source code?
It's in my fingers.
Oh.
There. I don't know the keys. I know the muscle memory.
I'm glad to have you here. Okay, so now, I have all these Forth words for updating slots by capturing data, find the max value of which slot has the highest occurrence in time, and so that kind of helps me select what the bearing likely is. And then there's a raw data buffer. I put data out at 500 times per second to a file on a flash drive, 65 gig flash. So it can run for a week probably, capturing 500 times. Oh, and it captures 32 bits, 500 times per second. And then after some processing, I prepare for sending out bearings over packet radio, AX 0.25, and that is requires, you can't, over ham radio, we can only go at 1200 baud, very slow. So when we set up this network of direction finding stations that we want to have, hopefully soon, this will report over packet radio. And if we're allowed to, at some, like one ham was going to be part of the network, said, no, I can't let you into my private home network. I don't want any hackers. So I can't use TCP/IP to pass raw data. But on command, by packet radio, I can ask, okay, at this time, this hour, this day, what bearing did you get? You know, so the thing will send me some packets over the ham radio. And okay, so let's see. Okay, you have to, I learned how to do files in and out. It took me a while, but oh yeah, and I have this little check stack CHKSP word that I wrote to, so in a lot of the code down here, where I have the captured bearings, for example, well, like here, where I just scan the bearings. So you see one CHKSP. Now, when I get this all working, I can probably get rid of those once everything's debugged. But while I was testing it, it was really useful to always have stack checks at that point in the program to see if I'm overflowing the stack or underflowing the stack. And let's see. Okay, and then I set up to hit letters on the keyboard here during debugging. So, for example, if I want to, oh no, this is something else. Okay, but I have like A, B, C, D. If I hit those letters, then it'll show me certain things going on. Okay, but this is something else. This A, B, C, D is just a list of things. So what we do is we first capture bearing, then process data and send out bearing. We have to wait for a strobe pin, wait about 20 microseconds for a strobe pin low and then high, and try to flush buffers while the processor is idle. And this processor is so damn fast, you can do that. I didn't need, at first I was thinking about using some multitasking Forth. Found out this thing's so friggin' fast, I don't need any I don't need no stinking multitasking. I just, in my own loop, I just take a moment out to write stuff to the disk or whatever. Okay, so once you get the strobe and you nibble, and then you get 4 bits of nibble, you process the data. Okay, well that's back there further. Then you keep looping around. You can try, I haven't fully tested this. You can dump data to the different buffers. You can send out data over the radio. I haven't written that yet, and it's still a work in progress. And anyway, to get back to this, oh yeah, so here's how, if you want to find where the word was, I like this. This is nice. You go like this. Okay, and you go Control C, Control F, Control V, find. Oh, okay. Find it again. You should get the definition somewhere. There. Okay. So you go down here, and what this does is, again, I keep checking the stack. Get consistent nibbles. Well, you can see what that does back here. Try to get consistent nibble again, because there's noise on the radio, and the 4 bits fluctuate. So you want to get them fairly consistent over a few microseconds or maybe 10, 20 microseconds. By the way, you couldn't do this with a PIC chip. Too damn slow. But this will do it. And so anyway, okay, then you do some checking. Is it within allowed offset of time? Then process the stable slot data, qualify it. And by the way, qualifying thing, I do a bunch of checks there. Control C, Control F, Control V, find. Oh, okay, that's for debugging. Control G, look for it. There, okay. So you do a bunch of stuff here. Oh yeah, by the way, fit a Lagrange polynomial to the slot frequency of occurrence numbers. And so I like an upside down parabola, and I get much more accuracy than, at plus or minus 22.5 degrees with these 16 LEDs. I can look for the peak of the parabolic curve. And so that's what this does. And I do another qualification. Okay, I do it on the peakiness of the curve. And if it's a good bearing, I terminate the qualified bearing, and I send data out as needed and so forth. Now, if it's unstable data, I do something else. I get rid of it, and anyway, kind of complicated. It took me months to write this, but I'm just getting slow at my old age. Let's see, what else can I say about this?
And you're up against a hard stop, so if you want to take a question or two.
Okay, yeah, let's take questions. I can get this radio back to the ham that lent it. How do you shut this off? Every radio's different. That woke you up. No questions? Hard stop, no questions, huh? Question. Yeah.
Don't touch the mic.
Oh.
Get your hands off of there.
Okay, you have 4 antennas. Now, do you sequentially sample each one?
No, the receiver is switched 500 times per second, one antenna at a time.
That's what I meant.
And
You're sequentially sampling.
And Bill Ragsdale talked about that, 2008. He wrote one with, it's called a Doppler Effect. You're wiggling the antenna back, you create an audio tone on the signal. You modulate, you have to use an FM receiver. And so the phase of that tone corresponds to the direction, and then there's a calibration knob, so in your car when I'm going hunting with these jammers on the radio, My wife stands in front of the car with HD, and I turn the knob so it points forward, and then I go hunting.
Your antenna looks like two cubes. This is a particular distance between the length of it?
Oh yeah, it's half-wave dipoles, a quarter wave apart. If you know, you have to understand electromagnetic theory to know why, but each antenna, to get the optimal is quarter wave. Okay, stop.
Done.
I have on my machine a browser page to an online check-in to the box for what you want to make. If you know what you want to have for lunch,